change of the length, u. So it has a natural some length. But when I will apply the load F, it will change its length by amount of u. So for example, if I'm using tensile force, then it will actually elongate, and this elongation is u. Now this elongation is proportional to the force. Bigger the force, bigger the elongation. And connection is a linear function. This is not always the truth in reality, but for small forces and small displacement, that is a good approximation, and this connection is written here as k times u. F equals k times u. What is this k? K is an inner characteristic of this spring. You may want to write it down. It is a spring constant. It is a spring constant. So that means that every spring has its own k. For example, if big K, then naturally for the same load, then displacement will be smaller, is it right? Again, for the same load, imagine I'm using 1 Newton. Then if K is big, then U will be smaller, because product should be 1. But if K is very soft, then naturally there will be a big displacement for the same load. So it actually shows how stiff, K says, how stiff the spring is. It shows how stiff is the spring. Bigger K means stiffer. The bigger, the stiffer. The bigger K, the stiffer the spring. Now, when I talk about 1 degree of freedom system, I mean that along this line, I need just one, this is a point, do you remember? So I need just one coordinate in order to know what happens with this mass. If I will know where this x of t is, then I know where the mass is, and I know the system. Because my system is a point on a vertical line. If I know x of t, I know everything about it. Because I don't need to know more about it. So it is like being 1 degree of freedom system means that is his curriculum vitae, so to say, or resume. His resume contains 1 sentence. I'm a point mass moving in vertical direction. That is it. That is an introduction of this mass to us, to the rest of the humankind. Okay, now solution. What does it mean, solution? We would like to write down an equation that governs the behavior of this mass. That is what I want. I don't want anything else. Now, before that I depicted it. There is a picture of the mass. Now I want mathematical picture, so to say. Okay, now let us do as follows. What we have to do is, let us follow some recommendations what we should do. Establish the reference frame and the displacement coordinate, displacement coordinate. Establish a reference frame and a displacement coordinate. That is what it says. Now we should make another picture of this mass. First, there is unstretched length of the spring. So when the spring is in normal condition, say I just went to machine shop and I asked, Mr. Machine Shop person, can you give me a spring? So he gave me a spring. So there is no mass acting on it, nothing. So it has a length. This length is called unstretched length. It is like length as is, as you purchased it, as you got it. Like length at delivery, so to say. It was delivered to you by the machine shop person. Okay? Now then, if that is a case, but then it vibrates, so then from this is an unstretched length, then there will be some displacements, u. Okay? There will be some displacement. Because I put now mass. I put a mass, so system displaced. Mass is point, but it has some value, okay? I just do not only do not like, but I'm unable to deal with a whole mass. Why? Because look, please, if I will take this binder as a mass, for example, then it depends when it is connected. Then it could rotate, not only go down, but it could rotate, etc. I'm unable now to deal with complex behavior of the whole binder. I would like to talk only about vertical motion. So therefore I say consider a possibility that this mass became a point mass. This whole binder became a point, but it has its own mass. The mass that it has is concentrated in a point. You may say, come on, that is not possible. Can you take a building and concentrate in one point? Are we magicians? That is correct. We are not magicians. We cannot do. But paper takes anything. You can write anything that you want in the paper. Later we will check, and we will see that our approximation or our, so to say, unallowed actions are not devoid of sense. They are, look please, by this vibration theory, we are sending space shuttle, and thanks God, space shuttle comes back. So that means that this theory is working. Unless there is some mistakes made, but then we are learning from mistakes, we are improving our knowledge, and then the reliability is increasing. That is what we humans always do. Okay? So what is the recommendation to do? That is, choose the x-axis along the line of motion and choose the origin. At the location where the spring is unstretched. This idea sounds so simple. I mean, choose the core x-axis, but before René Descartes, of French scientist, this was not known, and no one was able to write equations. And it was just very recently, relatively recently, just 400 years. 400 years ago, René Descartes came and said, please use coordinate system. Now every student, in the elementary school knows what is a coordinate system. Okay, so we are choosing x-axis along the line of motion and choose the origin x equals 0 at that location. There I'm saying that x equals 0, where the spring u is a displacement in x direction. Okay, we go further. Now we would like to draw free body diagram. Now what is a free body diagram? Free body diagram is a diagram of the body without constraints. In an arbitrarily displaced position. So pay attention, my picture is not very good. This Fs should be in the middle here. But what happened is I first wrote Fs, then I realized that I don't have a space to make a vertical line, so I made a vertical line on the left. Which shows, by the way, that professors are humans. You may not know that. To err is human. Okay, so Fs, now what I did is as follows. I told the spring, thank you very much for being here, but I don't want actually to deal with you. I will replace you, but your representative, your force, Fs, F sub s. I don't have a spring. I don't want to show so many things. Fs is spring force. Now we are coming to my friend, especially mine, because he took my name for some reason, Isaac Newton. Okay, we are using Newton's second law. Newton's second law says that there is this mass. This mass has an acceleration, u second derivative. This product equals sum of the forces. That is what Newton says.
It's u double dot?
U double dot, yes, which means second derivative or acceleration. Some young people who are driving the cars, indeed, they say that F equals mass times acceleration, and they F called fun. And they are driving with very big acceleration, but please don't do that, I'm asking you. Okay? So instead of force, they say it's fun to drive with high speed. That is not correct. Okay, so now what are the forces? We have just two forces. That's the outside force, F of t, and spring force. Spring, I said we chose direction. Direction downwards is positive. So F of t is this force here that acts upon the mass. Fs is a spring mass. Now there is also the weight. This mass, I said that this is a point mass, but it has a mass. I mean, I just took and crashed, so to say, this binder into a point, but I did not get rid of the mass. Okay? This is like when they make wine, you know, you take grapes and they are crushing these grapes. You know, smaller, it has smaller and smaller and smaller volume. It never becomes a point, but at least we see that it becomes with less volume and less volume and less volume. And then you get wine. So we have like then this f of t minus f of s plus w equals mu double dot. Okay. That is how we have to act. Then we go further. Now we relate forces to motion variables. Now we would like to relate forces to motion variables. How? F sub s equals ku. U equals 0 corresponds to unstretched spring. So that means that when I just got this spring from the machine shop and I put it there on the wall, at that point, before I put the mass, this was an unstretched length. Then we added, actually, we started to act, and we put mass, and it went down. So f of s equals, if u equals 0, then there is no, spring does not have any load. U equals 0 corresponds to unstretched spring. So then we got the following equation. Look, please. Fs is here on the left-hand side. I transfer it to the right-hand side, and the whole thing I'm transferring then to the left-hand side. So I will get m second derivative, then this goes to the right. Ku, this equals f plus w plus f. So look, please, we got suddenly differential equation. mu double dot plus ku equals w plus f of t. That is what happens with this mass. Now, by the way, pay attention, I did not get yet. My goal is to get u as a function of time. That is our goal. Please write down. Our goal is to find u. we are still very far from our goal, because instead of finding u, I found a differential equation for u. You may want to write this. We are still very far from our goal. Which is to find u of t. Now, what is this? First of all, it is a second order equation. Why it is a second order? Because u appears in the second derivative, u double dot. So this is a derivative. So it's a second order. It is linear. Why it is linear? Because u does not appear, we don't have u squared or u cubed or something like that. U appears in the first power. So it's a linear. Also, we don't have u times u double dot, then it would be nonlinear. Now, it is a non-homogeneous equation. Now, what is non-homogeneous? Right-hand side is not 0. And it is ordinary. Why it is ordinary differential equation? Because there is only time dependence. Ordinary means only one variable, not two variables, etc. With constant coefficients. What does it mean, constant coefficients? Mass. Mass, please write down, mass is a constant, k is a constant. You may say, do we ever have mass is not constant? Come on, just to come and say mass is constant. Why do I have to say such trivial thing? It is like saying 3 is constant. No, 3 of course is constant, I'm not going to tell you. But mass is constant. Mass is not always constant. For example, you can have a, yes?
Different places.
Say it again?
Different places. Different gravity. Right.
Yes, we could have, what else? And I will.
The weight varies, but the mass normally.
Sometimes weight varies. For example, we have some fuel tank, and then this fuel may be released for some purpose from the aircraft, for example. The mass of this fuel tank is changing naturally. Or we can imagine simpler case. Can you imagine something with a fly? So imagine that we have this mass, and fly is, sitting on this mass and leaves and comes and leaves. So mass actually is changing depending on that fly. Is it right? Just a very trivial example. So we are saying that we wrote there flies not allowed. So flies are reading and do not come to this mass. And mass is not changing. There is no release of fuel, etc. Fine, this is a differential equation. Now, this is dynamic equation, of course, because there is acceleration, etc.
And what about density? Can density vary in a body?
A student is asking whether or not density can vary in a body. Generally speaking, yes, density can vary in the body, but we got rid of this possibility because we said we are continuing a point, we are considering point mass. All the mass, maybe it was inhomogeneous, but we condensed it in one point. So we are strongest people in the world here in this room. We can take any mass and make a point. So once it is a point, then there is no density. Okay, now this equation is a dynamic equation, but it is also always interesting to relate it to static behavior. Now, what is a static behavior? Static behavior is a behavior when time is not involved. Now, what is a static behavior? If I had just weight of the mass acting on the spring, forget now additional loads, just weight, then there will be a displacement, which is weight divided by k. We know how do you remember we started our story by describing the spring, F equals ku. Now, because mass has a weight, then this weight W should lead to some displacement. So if there is only static constant, no vibrations, just because I put on this spring mass, Therefore, this spring should deflect more because I put some weight on it. It had an unstretched length. Then I put a mass. When I put a mass, it's a point mass, but it is a mass. Then it would displace. It would be displaced from that original position. What would be the displacement? It will be weight divided by spring constant. So that I call U static. I will call that static displacement, static, ST. I don't think there is any other professor in the world who teaches this so slowly. Why I'm doing it? Because we would like to catch basics extremely well. If we don't know basics, it's very difficult to deal with anything else. Therefore, I will proceed in the beginning, especially extremely slowly, almost statically. Okay? Any questions? Yes?
In this case, we have just only one force that is on weight spread.
Oh,
that's all.
look, pay attention. We actually have two forces. We have W and we have some other load. But I say, forget now for a second this load. Forget for a second that it is a dynamic problem.
Because we don't have outside force and we don't have acceleration at all in this.
Yes, then we will get this. Yeah, if I don't have this and acceleration I don't take into account, so then it will be Ku equals W, and then this U I'm calling static. It will be a static displacement. So now the main thing comes. Let the displacement of the mass be measured here. Let the displacement of the mass, here one word is missing, be measured, be measured relative to the static equilibrium position. And be denoted x of t. You may say, oh, I did not care that. But okay, you are just kind people. You are following me, and we will see that it was not very bad idea that we will do this. Okay. Now, that measurement, then I say, is, for me, I'm saying I would like to measure x of t will be, u of t will be x of t plus u static. What I'm saying is that I would like always to know, this is dynamic problem, but what would be if I would have solved it statically? Okay, if I would have solved it statically, I would get W divided by K. I would like to relate to it. Why? Because static solution is so simple. It's W divided by K. It's unbelievably simple. So therefore, I would like to relate to something which is so simple. You may want to write down what I'm saying because several reasons. For example, I did have several students in past years who took several different courses, and at some period they had to teach. And I heard that some of them at least adopted exactly my lecture notes. And one of them actually wrote me, oh, it was, I by chance write everything, and it was so easy for me to teach, it was unbelievable. So I'm recommending you to write everything. But I also, when I was a student, I would write everything, that prof would say. Why? Because I pay full tuition, so I better get everything. So why should I write less? Okay, now let us substitute in our equation. M, now I have U double dot. U double dot will be X double dot plus U static double dot. Now plus K. K times U, that is X plus U static. This equals W plus F of t. So I just substitute. Now look, please. Static is a number. So second derivative of a number is 0. K times u static equals f. So therefore this term and this term are cancelling. So w disappears. So I got a simpler equation. mx double dot plus kx equals f of t. There is no w. Had I not done this, what does it mean? Had I not introduced x of t with relatives to static displacement, I would always have a w because I made the mass point, but I cannot just say, let us forget its weight. Come on. If it is a point and has no mass, then it is not there. If it has nothing of the mass, if it has no characteristic of the real mass, then it is not there. If you get an ice cream that has 0 grams, I don't think that you are going to pay for it. So, very nice thing we are learning. First of all, what we learn is as follows. It is very important to work in a convenient coordinate system. Convenient. That is one thing, because in a convenient system, suddenly we don't have this W. Now, second thing is what is written here. The weight force can be eliminated if the displacement of the system is measured relative to the static equilibrium configuration. At this point, we finished our lecture, as I see there. 0, 0, 0, 0 means that is a rational number. That means 0 divided by 1. Okay, and I did give you an assignment. I think that I did not give to only one student or one listener this sheet of paper, which gives us the homework assignment. And you may want to rewrite, come here and rewrite the homework assignment, first 2. And I think that we will meet next Wednesday. I have a question. Do you get this, students who are enrolled, do you get these CDs? No, I'm just asking. Because first student came a bit, one student came a bit later, and I said, sir, how are you going to get this first 5 or 10 minutes? I don't know.
You can see it online.
Oh, you can see online. Then that means you are getting it if you can see online. Okay, first 10 minutes you are asking, so you can get it online. And you just I hope that you agree with me. Of course, it's very easy, and it will remain easy until the very end. Extremely easy. If it is wrong, then you tell me. Someone said it is easy to complexify, and it is very difficult to simplify.
It's from the last lecture, the last one.
And I think that you see also that this cost will be taken by the amenity part.
That's the period.
Yes.
So now we don't see anything.
It's almost like having,
Like-
two periods. Yeah, and then you need to find, what you call like a combined period.
First one, with the first one, right, and the second one, we'll meet again at the note, right?
Yeah.
Like this one.
Next Wednesday, right? Because Monday's a holiday.
Yeah, it's almost like, it's almost like the other functions, okay? But however, like the period varies within the